All right, guys. So what we're going to look at today is more, like I said, the mathematical part, kind of the very fundamentals of kind of movement in physics. We're going to look at the two categories that measured values can fall into. Okay, that would be vector quantities and scalar quantities. So if you've seen Despicable Me, okay, you remember the supervillain Vector? Okay, because his crimes had magnitude and direction. Okay, that's actually a real thing. Vector quantities have both magnitude and direction. Okay, so it's scientifically accurate. Unfortunately, he did not have a countervillain named Scalar, whose crimes would only have magnitude. Because that's the other thing. Okay, so scalar quantities are measured values that only have a magnitude. So, for example, my weight, okay, is a scalar quantity. Sorry, my mass is a scalar quantity, okay? I'm not going to tell you what that is, okay? But it's something in kilograms, and it's bigger than I'd like it to be, okay? That doesn't have a direction. That's just how much of me there is. I'd like there to be less, but that's how much of me there is. It doesn't have a direction. My weight, on the other hand, which is different than my mass, is a vector quantity, okay? It is about 785 newtons down, because my weight is the force of gravity pulling on my mass. Okay, so there actually is a difference between weight and mass, believe it or not. Okay, it's one of the things that in North American society we get really, really wrong. Okay, how much do you weigh? You tell them how much your mass is in kilograms. Okay, your weight is actually how much gravity pulls down on that mass. Okay, your mass is how much of you there is. Right, so when you go to the gym and you're either trying to lose weight or gain weight, whichever one you're trying to do, you're actually just trying to gain or lose mass. And you're trying to either make more of you or less of you. If I want to lose weight, I just go to the moon. I'll weigh 1/6 what I weigh here. There won't be any less of me, but I'll weigh 1/6 of what I weigh here. Okay? That might be a little extreme, but okay, it would work for losing weight. Okay? So the two things are different. Weight is a vector quantity because it's a force acting downwards. Okay, my mass is a scalar quantity. It's just how much of me there is. Okay, the ones we're going to look at today are going to be distance and displacement. Both of those measure, okay, how far something has gone. But one of them only cares about how far it's gone. The other cares about how far and in what direction it's gone from its starting position. Okay, so distance would be scalar. Displacement would be vector. Okay? Speed and velocity, not the same thing. Okay? They both measure how fast you're going, but one cares about also which direction you're going. So velocity is a vector quantity. Speed is a scalar quantity. Okay? Because I've never heard of anybody getting a velocitying ticket. Speeding ticket, yes. Velocitying ticket, never. Okay? They are not the same thing. All right? If you get pulled over by the police and they ask you how fast that you were going, do not give them your velocity. Because there will be follow-up questions, because this is what it would sound like. Do you know how fast you were going? Yes, sir. 138 kilometers per hour at 10 degrees south of west. And how much have you had to drink today? That would be the follow-up question, because that is a weird way to answer that question. When they ask you how fast you're going, they want to know your speed. They didn't ask how fast and in what direction were you going. If you were going the wrong way, that's a separate ticket. Okay, that's a much bigger deal. Right? So velocity has magnitude and direction, speed just how fast you were going. Okay, everybody with me there? All right. Okay, here's another thing we get really, really wrong in North American society, and it's about how we measure or how we talk about things. If I was to ask you how far it is to Edmonton, what would you tell me? 3 hours? 3.5 hours? Right? Is that what most people were thinking? Okay, what did I ask you? No, I asked you how far Edmonton was. But that's what we go to, right? If someone asks you, how far is it? You tell them how long it takes to get there. Is that the answer they want? It actually probably is. That's what we do wrong. Don't ask someone how far away something is if you want to know how long it takes to get there. Okay? Because let me tell you, I've gone to Edmonton a lot of times. And it takes a different amount of time every single time. But Edmonton is just as far away. Okay? Edmonton hasn't gotten further away or closer to here. All right? It is just as far away every single time, but it always takes a different amount of time to get there. All right? It can take anywhere from 9 hours, okay, to, I was not driving, 2 hours and 49 minutes. My friend was crazy, and I was much younger and stupid. Okay? Yeah, so it can be a pretty wide range because you might have to take into account road conditions. Okay? You get a blizzard that closes the road and you got to go off on the 2-lane roads and take you a long time. Okay? Maybe there's traffic. Okay? Things like that. Those can all affect how long it takes to get there. Okay? So we don't want to say, hey, if someone asks me how far it is to somewhere, I don't say 10 minutes. Okay? I say it's about 3 kilometers. All right? How far means something in meters or kilometers or something like that. The reason I bring that up is sometimes people mess that up on a question. Okay? The question was, how far is it? And they write a time. Because in North American society, that's how we've been trained. Okay? We understand that when someone asks how far it is, they want to know how long it takes to get there. Okay? That's just how we ask the question. Okay? In 25 years of teaching, I think I've actually gotten the correct answer in kilometers maybe 4 times. Okay? I've asked that question hundreds of times. Okay? But it's always just the way we're trained. Okay? So we want to understand that if somebody's asking how far, they want to know distance. If they want to know how long, then you can tell them it's 3 hours. Okay? Sort of make sense? Right? It's just we have to kind of undo some of the learning and training that we have had from society to look at how we do something properly in physics. Okay. So the way we describe things, okay, in North American society is kind of messed up. Okay, even European society is kind of messed up, although they're a little bit better, usually about giving something in kilometers, but they'll often tell you in a time as well. Okay, so let's say I'm standing here at Seldom Inn Campground, and I want to go here to Snake Indian Falls Campground. All right, and I ask someone else at the campground, how far is it to Snake Indian Falls Campground? And they tell me it'll be like 11 hours. How helpful is that? Not very helpful. How many choices do I have for which direction to go? 360. Right? If I pull out my compass, there are 360 degrees on that compass. Okay? One of those might get me to Snake Indian Falls Campground if I walked in a straight line and didn't lose track of it on the way there. Okay? Now, more practically, I would probably follow the dotted line, right? Because that would be a trail. So that would kind of work. Okay? But I'll tell you this, that's not a great way to tell people where someplace is. Because a friend of mine and I were hiking, and we did exactly that. And this is the embarrassing part of the story. We're both physics teachers. So we were hiking. It had been a long day. We hiked about 32 kilometers up and down passes. We were beat, and we were lost. Or we thought we were lost. So we sat down, we're looking at the map. We're out of water. There's no water to filter. We're getting kind of hangry. Okay? And all of a sudden, we're just, okay, fine. We're just going to start walking back. We know there's a campground that's going to take us a long time to get back there. We're going to walk back. At least we walk back. We're not lost. So we're getting ready to put our packs back on, and all of a sudden we see this guy, and he is running up the hill towards us with a heavy pack. Okay, now in retrospect, also wearing army fatigues. We didn't think about that much at the time. Okay, he comes up and we're like, dude, hey, did you come from Tumbling Falls Campground? And he looks at us like, oh yeah, Mike, it's just down the trail there, not 20 minutes, be there in no time. We're like, okay, awesome. An hour later, we stumble in to that campground. and we are cursing this guy. Okay, like we are like, okay, we're gonna get some food, we're gonna get some water, and we're gonna hunt that guy down, okay, because he told us 20 minutes, okay? And after we got some food and water in us, we started thinking a little more clearly, right? I turned to my buddy and I'm like, Sean, you know what we just did, right? And he's like, shut up. I'm like, no, man. He said, yeah, I know. We let somebody tell us how far away something was in time instead of distance, okay? In retrospect, we're two out-of-shape teachers on their summer vacation. Dude is probably like, you know, Aussie Special Forces out for a training run with his heavy pack. Okay, like very different situations. What was different between the two of us? He was really, really fast. We were really, really slow. We covered the same distance we did. If he'd have told us it was 3.5 kilometers, we didn't know it was going to take us an hour. Okay, because we know how fast we can walk. He told us 20 minutes, and we were tired and dehydrated. That's our excuse, and we're sticking to it. Okay, that, you know, he was going much, much faster than that. Okay, so we have to be careful about how we tell people where something is, because it can really, well, in some situations, be kind of dangerous. All right, so if I'm here at Seldom Inn Campground and I look, instead of asking somebody, I look, and on the trail there's a sign, and it says, Sneak Indian Falls Campground, 28 kilometers. Okay, did they give me a scalar description or a vector description? It just says 28 kilometers. Is that scalar or vector? It's scalar. It doesn't tell me which way to go. What does it assume I'm going to do? Follow the trail, exactly. Okay, guys, we use scalar descriptions all the time. Okay, all of our road signs are scalar descriptions. Okay, you get on the highway out here and it says, you know, Calgary, 32 kilometers. Okay, well, yeah. It just assumes you're going to follow the road, okay, that you're not going to, you know, go somewhere else. Now, if you're flying a helicopter, maybe that's less useful. Okay, maybe you'd like a vector description there. Okay, if you're, let's say, the navigator for a cruise ship, okay, if you leave New York Harbor sailing for Portugal, okay, does it do you much good if they say, yeah, don't worry, it's, you know, 700 kilometers. You're pretty screwed then because there's no roads to follow then. Okay, you kind of need a vector description. So one isn't better than the other. Okay, one isn't more accurate than the other, but they have their uses. Okay, sometimes one is more appropriate to use than the other. Okay, if you're going to be a pilot, a navigator, things like that, you're going to want vector descriptions because you're not going to be following roads. Okay, if you're a bus driver, follow the road. Okay, you can use scalar descriptions, then it will be fine. Okay, everybody with me on how that would work? Okay, because people get this idea, scalar's bad because it doesn't have as much information. Absolutely not true. Okay, a scalar value like distance can be just as good as displacement. Displacement's just always going to have that one extra piece of information. Doesn't always make it better. Okay, everybody all right with that idea? Okay, so if we say Calgary's 40 kilometers away, okay, we don't make a reference to which direction. I mean, obviously living here, we know where Calgary is, okay, but if we had told that to someone who's not from here, okay, it might not be as helpful to them, right? If we say Calgary's 40 kilometers away and it's, you know, directly north or 13 degrees west of north, okay, then yeah, that's useful, okay? But we've especially in our modern age become pretty dependent on stuff like this. Okay, we just punch it into Google, okay, and it tells us where to go. All right. Now, in Google, they actually give you quite a few useful bits of information when they do this, and all it's doing is exactly what we're going to learn how to do today. Okay. So, if I say I want to go to the zoo from here, okay, then it says, well, here's your possible routes. Okay, and it says via Highway 2, it'll be 42.8 kilometers, and it'll take 30 minutes. Okay? How did they figure out that it would take 30 minutes? I'm not even on the road yet. Any idea? Yeah, the speed limits. Actually, even now, they're even more accurate than that. Okay? You know that sign just up here when you go onto Highway 2? Okay, you just come off the exit ramp, says, you know, to get to the airport, it's this long. To get to downtown, it's this long. Okay? Do you know how those signs work? they take Bluetooth data from cars that pass. Okay, and there's stations along the Deerfoot and along Stony, okay, that'll tell you, and along McLeod, and it just keeps grabbing the kind of the what's the word, IP, okay, for your phone, okay, and it knows where you are, and it calculates how long it took you, or measures how long it took you, and then it can tell that information to people behind you. Okay, that's how it knows if there's a traffic jam, okay, or if there's a slowdown coming up or anything like that. Okay, it's taking that information. Okay, but on the very basic level, all that it does is this. It uses this very simple formula. V equals D over T. Okay, that is speed equals distance divided by time. Okay, now it does a few calculations along the way. Okay, so it would know that as we leave Holy Trinity here, okay, so as we leave here, that there would be a different speed limit along here, a different speed limit here, a different speed limit along all of these points. Okay, and it'll do a bunch of separate calculations. Okay, all the way along to tell you how long it would take. Now, that's where it comes up with this number from. Okay? It essentially manipulates this equation so it can solve for t. All right? When we use the mole equation, okay, was it basically the same kind of setup? Right? If we wanted to solve for m, we would move big M over to this side. Right? It's the same idea. If I want to solve for t, I want to bring t over to this side. Okay? So I'd multiply, right, both sides by t, and then I would bring v back over here. Okay? So I'd end up with this. T equals d divided by v. That's the calculation Google does in order to tell you how long it will take. Okay? Now, we'll go over that here a little bit more in a minute. Let's see if we can calculate what our average speed would be on this trip. Okay? I know it's going to take 30 minutes. Let's convert that to hours. How many hours is that? Half an hour. Okay. So we know Google says it's 42.8 kilometers. Okay? And that it's going to take 30 minutes. 0.5 hours. Okay? If I divide...
Please excuse interruption. Could the boys soccer team come down to the library, please?
Okay, so if I divide my distance, 42.8, divided by 0.5, okay, I should get 85.6, I think. Okay, all right, 85.6 kilometers per hour. How do I know I get kilometers per hour for my units? Yeah, well, that's what I divided, right? Kilometers divided by hours is kilometers per hour. Okay, that's what I had on the top, that's what I had on the bottom. Okay, everybody all right with that idea? Okay, now, are there parts of the trip where I go faster than 82 kilometers an hour? Definitely. But are there also parts where I go slow? Yeah. All right, so that's kind of like Google uses exactly what we're going to use today to figure out all that kind of trip data for you. How many people have used Google for that before? Okay, when you start driving a little more, you probably use it a little bit more. It's pretty handy because back in the day we had these big paper things, and it was really difficult to drive with them, right? And look at them and know where you were going. It was very dangerous to do that, so I didn't. And they were impossible to fold back up. Okay? They were called a map. I don't know if you guys have ever used that. Like you can't even find maps anymore, right? Okay, so that's what we're going to look at today is V equals D over T. Now, this is only one version of the formula. Speed is distance over time. Were there any directions in the math I just did? So all the stuff I used was vector or scalar? Scalar, right. Okay, the vector version of that formula looks like this. Same formula, okay, or it looks like the same formula. But on this one, you have velocity is displacement divided by time. Google doesn't use this. Okay, and I'll show you why in just a second. Okay, scalar descriptions are, in this situation, better because they're more realistic. I cannot drive in a straight line from HTA to the zoo. Okay, if I have a helicopter, I can fly it in a straight line, but I can't drive it in a straight line. Okay, so Google would not use this formula for me driving there because it would be like saying I did this. That black arrow would be my displacement. Okay? That is my change in position. It is how far and in what direction I will have gone when I get to the zoo. Okay? Everybody with me there? All right? It's still talking about the same trip. That's where I end up. Okay? When I'm at the zoo, this is what I did. I didn't literally do it, but it's how much I displaced myself from where I started. Okay? So it's the same trip, but from different points of view. And it can make it look really different. It can make it seem like you're not at all talking about the same thing. Okay? If you know Star Wars, it's kind of like this. Darth Vader betrayed and murdered your father. Darth Vader is your father. Okay? It's the same story, but from different points of view. Both are true. Okay? Darth Vader did betray and murder Anakin Skywalker. He also is Anakin Skywalker. Weird, but true. Okay? Just stories told from different points of view. Okay? He became a different person. He betrayed who he was and became someone else. Okay? So, that's true. And he also is this person. That's also true. Okay? Both are true. Okay? But they sound a lot different. These are both true as well, but they look a lot different. Okay? Because if I told you that for my going to the zoo, my displacement was probably okay. So Google says it's 42.8 kilometers. Okay? So when I drive to the zoo, I will have traveled 42.8 kilometers. I will also be 31 kilometers at 13 degrees west of north from where I started. Does that sound like the same trip? It is the same trip, but it doesn't sound the same because it's being looked at in a different way. All right. So, in your notes, does it still say more accurate? I keep forgetting to change this here, but I think I changed it in the notes. Does it say more descriptive description? Or does it still say a more accurate description? Directional description. Okay, good. So the notes are correct. Okay, so a more directional description, okay, would be Calgary is 40 kilometers away on a vector of 13 degrees. Well, I said east of north, there it should be west of north. Okay. Again, same description. One is not more accurate than the other. One has more information, but one is not more accurate. Okay? One is just looking at it from a vector point of view. The other is looking at it from a scalar point of view. Okay? Both are correct. Okay. Does anybody want that anymore? That's just what I did on the last slide. Can't be like that today, are we? Okay. So let's look at it from this point of view here, from a kind of a simple trip. Let's say we want to go from our house to Walmart. Unless you live right behind Walmart, there's no way to walk in a straight line from your house to Walmart. Agreed? Okay, so let's just say, hypothetically, we're talking about someone who lives in like Darcy. Okay, so just over here or something like that. Okay, so if you lived in Darcy, okay, and you wanted to go to Walmart, let's say you walk. Okay, so you walk and you have to kind of go out and you got to get on Northridge Drive, and then you got to follow Northridge Drive, cross the railroad tracks, cross the river. Okay, then you're on Southridge Drive, and then you got to go over to Walmart. Okay, so you can't walk, you can't go in a straight line. Okay, you can just do that. You have to follow the roads. You can't walk through people's houses and walls and trees and things like that. Okay, so that's what you have to do. Let's say, just for argument's sake, that is 4 kilometers. Okay, so you've got your watch on, okay, and it's tracking your steps and your distance and everything. When you get there, you look at it, it says you've got exactly 4.0 kilometers. Okay, by the way, if you haven't got this, write this down. Okay, draw this picture. Okay, follow along. This is going to be our scalar versus vector example. Okay, so when I get to Walmart, my watch says I have gone 4 kilometers. Distance or displacement? That is distance. That's how far I went. Okay, I went a whole bunch of different directions. That's how far I had to walk. Okay, let's also say that I'm a fast walker. And that only took me 0.5 hours. My light karma was really good. I didn't have to wait for any lights or anything like that. Okay? All right. Can I calculate my speed? I can. Okay? If I say, all right, speed is distance over time. Incidentally, this is on the back of your periodic table. All of the formulas for physics are on the back of your periodic table. Okay? So you're going to need that for this unit. Okay? All right, so V equals D over T, 4 kilometers divided by 0.5 hours is going to give me a speed of 8 kilometers per hour. That's fast walk. It's like one of those speed walkers. Okay. All right. Now, if I look at this from a vector perspective, okay, this is what I've done. Sorry, I'm just going to make that a different color. All right, from a vector perspective, that's what I did, right? And let's just say that that is, .7 kilometers, and I'm going to say it's about 40 degrees south of east. All right, is that a vector description? Does it have magnitude and direction? Okay. How long did it take me to do that? Are we still talking about the same trip? I walked to Walmart. How long did it take me? A half an hour. It doesn't matter whether I'm talking about displacement or distance. Time applies to both. Okay? Incidentally, time is also scalar. Okay, time is a scalar quantity. It's another thing we mess up in North American society. Okay, if I ask you how far is it to Edmonton, you'd be like, it's 3 hours north of here. Okay, time is not a vector quantity. We don't put direction on time. Okay, we don't say that summer holidays is 6 weeks east of here. Okay, it's stupid. We just don't do that.
Please excuse the interruption. Could all badminton players go to the library for pictures? Thank you.
Okay, so time is the same. It took me half an hour. Can I calculate my velocity? Yeah, okay. This is where I use this formula. Velocity is displacement divided by time. So 2.7 kilometers at 40 degrees south of east over 0.5 hours. Okay? So I will get that my velocity is 5.4 kilometers per hour at 40 degrees south of east. Because velocity is a vector quantity. So it needs magnitude and direction. Is it just a coincidence that the velocity vector is the same as the displacement vector? Okay, if you're confused by that question, let me ask you this one instead. If I travel 100 kilometers per hour west for an hour, can I end up north? Okay? Your velocity and your displacement will always have the same vector. They have to. One causes the other. Okay? By traveling at 5.4 kilometers per hour at 40 degrees south of east for a half an hour, I ended up 2.7 kilometers 40 degrees south of east from where I started. Okay? They're always going to have the same vector. It is not by accident, it is on purpose. Okay? They have to share the same vector. Okay, does that part sort of make sense? Okay, same trip, looks a little bit different. Here's where it gets crazy. Let's say I get to Walmart and I realize I've forgotten my wallet, my phone, I have no way to pay for anything, so I don't even bother going in. I turn around and follow exactly the same path all the way back home. How far have I gone now? It's 4 kilometers to get there. How far have I gone now? 8 kilometers, right? My total distance, if we're talking about the whole trip, will be 8 kilometers, all right? And it took me a half an hour to get home. So I walked 8 kilometers in 1 hour. What's my average speed? 8 kilometers per hour, distance over time, 8 over 1, okay? 8 kilometers per hour. Here's where it gets weird. What's my velocity if I go back home? Remember, displacement, that D that we wrote there, the 2.7 kilometers at 40 degrees south of east, that's your change in position. How far and in what direction you have gone from where you started. So, if I go back home, how long is that arrow? Have I displaced myself at all if I end up back where I started? What's my displacement over the whole trip? 0. What's my average velocity over the whole trip? 0, right? If velocity is displacement divided by time and displacement is 0, I get no velocity either. Okay? This is where they start to look really different. I walked 8 kilometers. It took me a whole hour. But from a vector perspective, I accomplished absolutely nothing. I ended up right back where I started after 1 hour of walking, and my displacement is 0. My average velocity is 0. Okay? Same trip, 2 different points of view. All right, so does that mean that sometimes scalar descriptions are better than vector descriptions? Yeah. The odometer in your car, okay? Does that measure distance or displacement? The one that says how many kilometers are on your car, does that measure distance or displacement? Distance. How useful would it be if it measured displacement? Well, it would be great if you're trying to sell your car. Okay? Because what would it show every time you come home? No, it would read however far it is from the dealership you bought it at to your house. When you drive back to the dealership, it'll read 0. True. Dirty question, but okay. Yeah, it would, let's just say effectively it would read 0. Okay? What if you've driven that thing into Calgary every day for 5 years? Does it actually have 0 kilometers on it? That's exactly why it shows how far you have driven it and not how far it is from where it started. Okay? Because otherwise every day it's going to say it's brand new. Okay? And it's totally not brand new. Okay? So in lots of situations, scalar is superior, and in other situations, vector is superior. It all depends on what you want to do with it. Okay? All right. That making some sense? Comparison? Okay. All right, so this is just the word notes for what we just did. Slightly different numbers, okay, in there. So 4 kilometers from the house to Walmart, okay, so okay, if you go to Walmart, you're 2.8 kilometers in a straight line, but you actually have to walk 4 because you've got to avoid things, okay. Distance is always going to be either greater than or equal to your displacement. Distance can never be smaller. Okay? The only time they can be equal is if you walk in a straight line. Exactly. The only way distance and displacement can be equal is if you actually walk in a straight line. Okay? Give you an example. Okay? I'm going to walk in a straight line right along this seam in the floor. All right? I'm going to walk 4 meters that way. Okay. Is my displacement 4 meters west? Is my distance 4 meters? Okay. What's my distance now? 8 meters. What's my displacement? Right. Okay, everyone follow? Okay. You're never going to have to do ones more complex than forward and backward, east, west, north, south. You're never going to have to do any with angles because that brings trigonometry in. Okay, and we don't know if you guys have done trig in math yet. Okay, when you take science, so you won't have to do any trig in science 10. Physics 20 is the thing we do day 1. Okay, we do the trigonometry version. Okay. So this is the notes part of, okay, what it would look like if I went to Walmart, calculating the speed, calculating the velocity, so all the stuff we did on the example, okay, and then if you went the same route home, okay, well, when you get home, your displacement is 0, your velocity is 0, but your speed and your distance have gotten larger still, okay? Distance always gets larger, okay? Displacement can get larger and smaller. All right, using V equals D over T. So, got some algebra to do. Just a tiny bit more than what we had to do with the mole equation formula. So, a quick review from chemistry when we learned the 3 rules of algebra. Okay, rule number 1, if I want to move something, I do. Heard somebody whisper they were right. If I want to move something, like let's say I want to move t. Right now I'm dividing by t, so if I want to move t to the other side, I have to. Right, so if I want to move something, I do the opposite. Okay, that's algebra rule number 1. Okay, algebra rule number 2, what I do to one side must be done to the other side. The golden rule of algebra. Okay, and then the 3rd rule of algebra, we didn't have to use in chemistry. We don't have to use it for this formula, but we will for our next one. Okay, and that is move what's not attached to what you're looking for first. We'll talk about that third rule in just a minute. Okay, so if you've been using a triangle to help you with algebra, you can stop that right now. Triangles are done, okay? We don't use triangles in physics because after this formula, they stop working. Okay? They won't work for any of the other formulas we use. I want to solve for d. How do I get d by itself? Multiply by t, right? Okay, if I want to move something, I simply do the opposite. Okay, so I multiply both sides by t comes over there, and then I'm multiplying to get d. All right, so let's say that v is in meters per second, t is in, t is in seconds, and d is in meters. Okay, so if I take my seconds and I multiply by meters per second, because that's what I'm doing, right? Time times speed, so s seconds times meters per second. What are my units going to be for d? Meters, because the seconds are going to cancel. Okay, you can always double check if your algebra was right by just plugging your units in to see if it worked. Okay. All right. Okay, let's say I want to solve for t. How many people are feeling right now like they need to move d right now? Okay, here's going to be the problem with that. If I want to move d over to the other side, I have to do what? Right now d's on the top. If I want to move d over, if I multiply by d, what's d times d? D squared. That doesn't help me move it, does it? Okay, so if I want to move d, I actually have to do what? Divide. Okay, what's d divided by d? Right? 3 divided by 3 is 1. 2 divided by 2 is 1. D divided by d is anything divided by itself is 1. Okay, so if I do that, here's what it leaves me. Okay, d would come over here, because what I do to one side I have to do to the other. Okay. Leaves me with 1 over t. Is that the same as t? Is 1 over t the same as t? Okay, if you're nodding yes, let me ask you this. Is 1 over 2 the same as 2? Then 1 over t is not the same as t. Okay, because 1 over 2 is 1/2. That's definitely not the same as 2. Right? So doing that didn't work. It got me 1 over t. So here's what we do instead. Okay, believe it or not, what I want to do is move t. Move t over here. I want to multiply both sides by t. You can never solve for something if it's on the bottom, because you'll always solve for 1 over it instead of it. Okay, so if something's on the bottom, you can't solve for it until you've moved it to the other side and put it on the top. Okay, so now t is over here, but I'm trying to solve for t, so what do I have to do with v? Yeah, move it over, right? Right now I'm multiplying by v, so to move it I would divide by v. Okay, now I've got d over v. That would be meters divided by meters per second. Meters are going to cancel, I'm going to be left with seconds. Is that the units for time? It is. Okay, everybody all right with that? Okay, so we're going to do a little algebra practice, okay, but that's all the manipulation you have to do for this formula, okay? Solving for, it's already solving for v. If I want to solve for t, I move it over here, I bring v over, okay, just like we did with our mole equation stuff, okay? Pretty simple, okay, for us to do. Okay, so I did have you write these down in the chemistry unit, but in case you've lost that part of your notes, okay, I want you to write down the 3 rules of algebra here, put a big circle around them in your notes, okay, so that when you're kind of learning how to do all of this manipulation, you have something to refer back to. Okay, so just give you a couple minutes here to get those written down. So let's look at a formula that we're going to use, okay, here going forward, just to kind of show you how these rules work, especially the 3rd rule since we haven't done that one yet. Okay, you may have seen this formula in math. Okay, it's the equation for a line. Okay, y equals mx plus b. Let's say I want to solve for m. What should I move first? B. It's not attached to m. X is attached to m. B is not. Okay? So if I want to move B over to the other side, what do I have to do? Subtract. Okay, so B minus B is 0, not 1. Okay? And so we would have y minus B equals m times x. Okay? Now what do I do to get m by itself? Divide by x, right? Okay, all we did was follow the rules of algebra. Okay, pretty straightforward. All right, later on in this unit, okay, we'll be using this formula. Okay, let's say I want to solve for VF. What should I move first? What's attached to VF right now? VI is attached to VF, okay? Because I would have to subtract those two, all right? So T is below them, below that. So if I want to move T to the other side, what do? Multiply both sides by T, okay? So T cancels there, T comes over here. I want VF by itself. What do I do with VI? Right now I'm subtracting VI, so to move it I would add it, yeah. So I would have T times A plus VI equals VF. Okay? Not terribly difficult. Right? I'm just using those 3 rules of algebra. Okay? Those 3 rules of algebra, okay, will get you through high school physics, high school chemistry, no problem. They'll even get you through any university course, science course, physics, chemistry, that's not based in calculus. As long as it's linear, okay, you'll be fine with those 3 rules of algebra. Once you get into calculus, forget it. It's a totally different animal. Okay, but as long as it's linear stuff, those 3 formulas will work, or those 3, rules will work. All right, I want you to write this one down, and we're going to kind of walk through it together here. Okay, first V equals D over T kind of question. Okay, so in any physics question, okay, and this one's very simple because there's no really long story to read here, okay, what we want to do is, just like what we did with mole equation questions, we want to write down our givens, all right? So, how far will a deer run? Okay, what am I looking for if I'm looking for how far? Distance, right, okay? So this question wants me to solve for D. Okay, now it says the deer is running at 15 meters per second. What did they give me there? Speed. Yeah, it's how far or how fast it's going, right? Meters per second. All right, so that would be our speed. How do I know that's not velocity? How do I know that's speed and not velocity? What did they not give me there? No direction, right? Okay. Velocity would have magnitude and direction, be 15 meters per second east or something. Okay, it didn't give me that, just said 15 meters per second. Okay, and it tells me that the deer runs for 45 seconds, so they just gave me time. Okay, now obviously the story part of the questions will get increasingly complex as we go along, but what you have to do is kind of pick things out. Okay, context can tell you what something is, but units can also tell you what something is. If it's in meters per second, kilometers per hour, centimeters per year, whatever, if it's a distance over a time, it's going to be speed, okay, or velocity. And if it's just in meters or kilometers or whatever, that's going to be a distance or a displacement. Okay, and obviously it's in seconds, minutes, hours, days, then it's a time. All right, so I've got the time here, 45 seconds. So I'm looking for D. Obviously, the formula I would use is going to be V equals D over T. All right. Now, that's not set up to solve for D. How do I get D by itself? Multiply both sides by T. Right. So, okay. That's supposed to be a multiply times T. Okay. So T comes over here. All right. T times V equals D. All right. So if you were, like, if this was a question you were doing on a quiz, that would be 1 mark. Okay. The original formula would be 1 mark. Your manipulation would be another mark. Okay, and then you would have your 45 seconds times 15 seconds equals D. All right, so that deer is going to run 675 meters. Is that fast? Yeah. Okay. To give you perspective, the world's fastest human runs at 17 meters per second. But he can only run that fast for about 30 seconds. Okay. So he would run, well, pretty fast. Okay. Pretty far, 200, 400 meters maybe. Okay. But yeah, this is pretty insanely fast, and they could keep doing that for a very, very long time. Okay. Everybody all right with that idea? All right, questions there? Okay, pretty straightforward stuff, right? All right, write this one down, give it a try, okay? We'll walk through it together in a couple of minutes here. Okay, let's have a look at this one. So if they're asking how long something's going to take, what do they want me to solve for? Time. Yeah, time is how long things take. Okay, so always looking for a contextual clue in the question. That's it. Okay, how long will it take a tortoise to crawl 200 meters? What did they give me there? Distance. How did I know it wasn't displacement? There's no direction, right? It just said 200 meters. It didn't say 200 meters downhill or something like that. It just said 200 meters. Okay, at a speed of 0.25 meters per second. Well, obviously it's speed because they said so, so I don't have to think too much about that one. 0.25 meters per second. That's supposed to be fine. Okay, so I'm looking for T on this one. All right, so V equals D over T. So again, if this was a quiz, that would be a mark, and so would that. Okay, the reason you get a mark for picking the right formula is by the end of this unit, well, if you look at the back of your periodic table, there are a lot of formulas to choose from, and so there's a mark for being able to identify what type of question you're working on. Okay, now I'm trying to solve for T. Right now, T is on the bottom, and I can't solve for things when they're on the bottom, so I need to move T to the other side by multiplying it over. All right, so multiply both sides by T. T cancels over there. T comes over here. Good. Now I'm set up. So I have to solve now. I have to get rid of V. So how do I get V over to the other side? Divide, because right now I'm multiplying by V. Okay. So my final formula there is going to be T equals D over V. So that's going to be 200 meters divided by 0.25 meters per second. What's going to happen to the meters when I divide that? They're going to cancel. Right, and I'm going to be left with seconds. All right, 200 divided by 0.25 should be 800 seconds, if my mental math is okay. Is that a long time? Yeah, it's like 60. It's like 3-something minutes, something like that. It's a long time. Okay. No, sorry, it's way more than 3 minutes.
It's
800 divided by 60. Yeah, it's 13 minutes. Sorry, 3 minutes. 13 minutes. That's a long time to go 200 meters when a person could run it in 18 seconds if they're an Olympian. An average person probably take about 30 seconds. All right, questions on how that one worked? Okay. Now, all of these so far have been scalar questions. Okay, it does change a little bit when we start having to deal with vector questions. All right, so here's a vector problem. I want you to copy this one down. We're going to walk through it together so we see a vector problem solved. So this bus is going to go 100 kilometers north, and it's going to take it 1.2 hours to do that. Then it's going to turn and travel 62 kilometers south in 0.9 hours. Does this sound like two separate trips? Right? Because first it goes north, and then it goes south. So it backtracks. Right? If I was watching this from above with a drone, okay, what I would see is the bus do this, okay, 100 kilometers, and then I would see it come back 62 kilometers. Okay? How far has that bus gone? 162 kilometers. That's the bus's distance. That's scalar. Distance doesn't care what direction I go. Okay? But that's not what this one wants. It wants the average velocity. Well, if I want to get average velocity, I need displacement and time. In fact, I need the total displacement and the total time. Okay? So this is going to be my average. Okay? So can I figure out, okay, what my total displacement would be? Remember that displacement is your total change in position from your starting point to your end. Well, that's going to be part of my time at 0.9 hours, right? 38. Which direction? Okay, so I went north 100, came back 62. Am I still north of where I started? Yeah, because here's where I started. Okay, I started right here. I went 100 kilometers north. I came back 62 kilometers south. Means I ended up right here. Okay, I am still 38 kilometers. So you're right, Angela. Okay, 38 kilometers north of where I started. Okay, you see the diagram I drew there with the two arrows? Okay, that's how we draw vectors. It's often helpful to have a visual representation of the trip. Okay, I clearly went further north than south. So I still ended up north of where I started. Okay, we call this a tail to head diagram. We use them all the time in Physics 20. Okay, we don't use them as much in Science 10 because we don't go off to the right or the left ever. Okay, they're just always kind of backtracking. Okay, so my total displacement, okay, so I'm just going to write dt there for displacement total, is 38 kilometers north. All right? What's my total time? When I was traveling north, that part took me 1.2 hours. The south part took me 0.9 hours. 2.1 hours. Now, I subtracted the displacements. Why did I add the times?
You can't go back in time.
Exactly, you can't go back in time. If I subtract the 0.9 hours from 1.2, then it says I went back in time. I can't make time essentially negative. Okay? You're never going to subtract time. Time is always going to go forward. Okay? As far as we know anyway, okay? For our experience, okay? Time moves in one direction only. That's why it's a scalar quantity. Time only passes. It doesn't go left or right or south. Okay? So our total time here would be 2.1 hours. Do I now have everything I need to get my average velocity? So average velocity, okay, so the V with the arrow over top, okay, is going to be our total displacement, 38 kilometers north, divided by 2.1 hours. Okay, and that's going to give us 18.1 kilometers per hour north. I have to have that vector on my answer, because velocity is a vector quantity. Okay, so that worked a little bit differently than the ones we did previously, because direction mattered in this question. Okay. When I first asked you, what's the total distance traveled, I got the answer right away, right? It was 162 kilometers. You went 100, then it went 62, you went 162 kilometers. Scalar stuff is easy. It always gets bigger. Okay, just keep adding it on, just like the odometer in your car. Okay, the odometer in this bus would have shown 162, because that's how far it went. Okay, but if I was watching it from above, it only ends up, after doing all of this, 2.1 hours later, it's only 38 kilometers north of where it started. Okay, that's where the vector stuff and the scalar stuff operate differently. Okay, sure, plugging it into the final formula is pretty similar, but how I get the numbers inside is a little bit different when direction matters. Okay, essentially what you have to do is say, north's going to be positive, south's going to be negative, and I'm going to move them together. Okay, or right's going to be positive, right's going to be positive, left's going to be negative, okay, and I'm going to combine the two together. Okay? All right. What do we got for time here? Okay. So, for this week, guys, tomorrow you're going to mostly just work on some problem solving to do with this. Okay? We're probably going to move on to some graphing stuff by the end of the week. This week's quiz, okay, will be on the stuff from before Easter, so energy, okay, thermodynamics, that stuff, and V equals D over T. I'll put the practice quizzes up right now so you know which ones you need to look at. Okay?